Last video I made a brief reference to area. I want to say a little bit more about here. So we're going to find sine area. The sine area between the graph of f and the x-axis over the interval a to b is simply defined to be the definite integral here from a to b of f of x dx. So sine area, once again, so this area above the x-axis counts as positive. This area down here counts with a minus sign. So to find the sine area here, this is a to b, the definite integral from a to b of f of x dx would simply be the area of this region plus the area of this region minus the area of this region, because this region is coming with minus signs. So at this point, we want to start thinking about what are some answers for what definite integrals are. And so sometimes we'll be able to calculate out definite integrals very quickly if we have nice, simple geometry in terms of rectangles, triangles, circles, stuff like that. So for example, let's compute the integral from 0 to 5 of 3 minus x dx. And let's draw a picture of this. 1, 2, 3, 4, 5. So we're going from 0 to 5. When x is 0, 3 minus x is equal to 3. Straight line, slope minus 1. So this is our graph of our function. And so this definite integral needs to equal this area here, but then we have to subtract off this area down here. So let's calculate out what these areas are, and we can just do this using high school geometry. So this area of this triangle, so this is a 3 by 3 triangle. So its area is 3 by 3 divided by 2. This triangle is a 2 by 2 triangle. So the area is 2 times 2 divided by 2, and it needs to come with a minus sign here. So what is our answer? 9/2 minus 2 is going to equal 5/2. One more example of things like this. Let's do an integral from 0 to 5 of absolute value 3 minus x dx. So this is different here because now we have an absolute value thrown on. So between 0 and 3, the function looks just like as it did before, but now it starts increasing between 3 and 5. So here, the entire thing is above the x-axis. The areas of the respective triangles are the same. However, they both come with plus signs here. So now this answer is going to be 9/2 plus 2 is 13/2. Okay, so this is a good example with a particular function. Let us calculate out some particular integrals here for x, the integral of x, and the integral of x squared. And we're going to do this in a couple of different ways. So the integral from 0 to b, now we're going to try to come up with a nice general format here of x dx. So the graph of x dx is a straight line with slope 1. So this is b here. We're trying to find this area. So this area simply has base b, height b, and so the area here is just b squared divided by 2. So now we know exactly what the integral of x dx evaluated between 0 and b is. One more formula here. That will be the most complicated one in this set of videos. The integral from 0 to b of x squared dx. So so this is going to be integrable from before, and so we're going to use our right endpoint approximations from before to evaluate this definite integral. from before, we know that, so go back to our definition of integrable. Our function integrable if every single Riemann sum approaches the same limit here, and we have a continuous function, so it's guaranteed to be integrable. So this means that we can choose any approximation we want to in the limit in order to do the trick. So what we're going to do, let's make the decision to choose the right endpoint approximation here. So when we choose the right endpoint approximation, so our interval is 0 to b, and we want n subintervals. So delta x is going to be b minus 0 divided by n, which is just b divided by n. Our xi points are going to be 0 plus I delta x. So that's, more generally speaking, a plus I delta x is 0 plus I times b over n is just I times b over n. And so our approximation, R sub n, is the sum from I from 1 to n of, we plug in IB over n into our function, IB over n squared, and we also have to multiply by delta x, which is b over n. So what do we see here? We end up with, so there's a b squared and another b, so a b cubed, we can move outside the sum. We're dividing by n squared, we're also dividing by n, so we can move out an n cubed outside our sum. So now we're just left with the sum from I from 1 to n of I squared. So this is one of the power sums that we know from before. So this is n times n plus 1 times 2n plus 1 divided by 6. So let's recopy that with a limit here. We want to take the limit as n goes to infinity of b cubed over n cubed times n plus 1 times 2n plus 1, all of that over 6. We could do this using L'Hopital's rule. I'll just kind of quickly note that we can just look at the leading terms here. We have 2n cubed upstairs times a b cubed. We have n cubed downstairs times 6. So just looking at the leading terms, we end up with 2b cubed divided by 6, which is just b cubed divided by 3. So what do we observe here? What is our conclusion? Integral of x squared dx from 0 to b is b cubed over 3. Also, the integral from 0 to b of x dx from before was b squared over 2. And if I'd say, what's the integral from 0 to b of x to the 0 dx? That's just 1. That's just b. So something you should be noticing here, there's a little bit of a pattern here. The integral of x to the 0 gives us b. The integral of x gives us b squared divided by 2. The integral of x squared gives us b cubed divided by 3. And so it is reasonable to think, what do you think this is going to equal to? And so a good guess that turns out being true is that the integral of x cubed is b to the 4th divided by 4. So that is something you can think more about. This, go home, try to do this yourself. It's a kind of fun little exercise to do here. But let's wrap up this video with a pre-class problem. Just have you do some. For this one, you don't want to use the formulas I just presented. You can do this with geometry here. Here's just 2 definite integrals for you to compute.